again, I'm back to revisit my 4-to-1 mux, and I want to show you yet another way to implement it. So if you recall, the first way we implemented the 2-to-1 mux anyway was using those gate level specification. So we use the gate primitives like and, or, not. So those are built into Verilog. And then we found that a little bit unwieldy because that requires us really to just sort of translate from schematic to Verilog, which, again, if we have to go to the trouble of deriving a schematic and then, translating that into Verilog, we haven't really gained anything in terms of efficiency of design. So maybe we've saved ourselves the wiring, but we still had to come up with the resulting schematic. So then the second thing we did was we came up with a Boolean expression, and we specified that Boolean expression for the 2-to-1 mux. So that's what we ended up with here. And that ended up being quite efficient, and for simple circuits is perfectly reasonable and a very valid approach. But I'm going to show you a different kind of specification called a behavioral specification, and this is useful especially for more complex logic designs. So recall that last time we discussed when we were talking about simulation, we used this, what we called a procedural block, and that was the initial block. And recall that in this procedural block, we said that it differed from our regular kind of Verilog statements in that the processing wasn't concurrent. It wasn't, when you were writing, for example, in your 4-to-1 mux, and I'm instantiating things, and maybe I'm assigning values to signals and whatever, all that is happening concurrently at the same time in parallel. But in an initial block, and as we'll see in this new kind of procedural block that we'll talk about called an always block, the order in which we specify the statements is important. And I use the initial block for simulation purposes. So I generally, you're not going to use the initial block outside of a simulation. But this always block is a lot more flexible. So initial specifies the initial conditions for the simulation. The always block, however, can be used in my design source, so not just in my simulation source, and it will always be executed, as the name implies. And again, everything inside the always block is executed procedurally or sequentially. So it very much matters the order in which you write your statements inside an always block. The other valuable thing about the always block is that when I can only use behavioral specification inside an always block. So this includes logical constructs that you may be familiar with from high-level programming languages, like if-else control blocks, any kind of conditional logic, loops, for example, which we'll get into. All those things can only be specified in Verilog inside a procedural block. So in our case, it will be inside an always block. So again, to distinguish the two, so there are a couple of distinctions. So both initial and always blocks are procedural, like I said. Initial, however, is really only used for simulation, whereas always can be used in design as well. So it can also be used in simulation, but also in the design source. The other similarity about them, so before I get into another difference, the other similarity about them is recall that we said that any signal that is being assigned inside a procedural block, so inside our initial block, we assigned the signals X and S last time. And we said that any signals that are being assigned values inside a procedural block have to be declared as type reg. So if you are not assigning a signal, if its value is not being assigned inside a procedural block, then it could just be a regular input, output, or wire. But if it is being assigned inside an initial block, or in our case now, as we'll talk about, an always block, then it must be declared as being of type reg so that it retains its value until you assign it a new value. So that is another similarity. However, the difference, coming to a second difference between the initial and always block, the always block specifies what's called a sensitivity list. So this is a list of signals, a change in which will trigger the always block to run. So let's start with an example. So I'm going to rewrite my 4-to-1 mux, and I'm going to write it using behavioral specification. So what I'm going to do is I'm going to get rid of all this. And rather than delete it, I'm just going to comment it out so that we can see the difference. So in this new implementation of my 4-to-1 mux, I am not going to use any 2-to-1 muxes anymore. I'm just going to specify its behavior. So how I'm going to do it is the following. So my general approach is that I want to assign y a different value, a different bit of x, based on what my selector is. So I'm going to assign the value of y, my output, based on certain conditions, input conditions. And because I'm going to assign my output y inside a procedural block, which is my always block, so again, my logic goes like this. I'm going to use a behavioral specification. Therefore, I need a procedural block. I need an always block. Now, because I'm going to assign y inside this procedural block, y needs to be declared as being of type reg. So if you'll recall, in the simulation file, I just had regular registered signals, and they were not inputs or outputs because simulation files don't have inputs or outputs. But in this case, y is an output and it's also registered. So the way I specify that in Verilog is I'm adding this keyword now called reg. So I'm declaring y as it's still an output, but now it's also registered. So now I'm going to specify my always block. And here's what I mean by a sensitivity list. So the way I specify my sensitivity list is I have an @ sign after the always, and then I follow it with a comma separated list of signals, a change in which will trigger my always block to run. So if any of the signals inside the sensitivity list change, it will trigger this always block, or the logic inside this always block to run. So in my example here, I want my y output to change anytime either x or s. So anytime my input or my selector changes, I want those changes to be reflected in my output y. So I am going to specify here x and s. Those are my signals. And then I'm going to start with a begin and an end. So I'm going to encase all my code inside this begin and end. And now I'm going to indent. So notice like my indentation, I'm very specific or very particular about indentation because I feel like it's just a really easy way to sort of visually see the structure of your code. And that makes it easier to debug. I can at a glance see what code belongs in which blocks. So notice my module and my end module are at the same indentation. So they're all the way here at the left margin. Then I have everything else is indented like by one tab character. And now inside my always block, I'm going to indent all the code inside my always block to indicate that everything in this code belongs to my always block. So the first thing I'm going to do, and I'm going to do this two ways. So let me show you the first way that I'm going to do it. So the first way, I am going to say if S, my signal S, is equal to, and let's have a word about this double equals. I'm going to explain that in a second. But if X is equal to the value 0, so I specify that with 2, meaning it's 2 bits wide. B, so the apostrophe is, that's part of the syntax. So the 2 specifies how many bits wide my signal is. Finally, the B specifies the radix. So in other words, the base. In this case, it's binary. But if I want to use hexadecimal, it would be H. I could use O for octal or D for decimal. So if S is equal to the value 0, so I can specify it like this, or I can just specify it like this, to be 0, which is, and those two are equivalent because Verilog will pad all unspecified bits with 0. So if S is equal to be 0, I didn't mean to put a semicolon there. And I'm going to close my parentheses. And I'm going to just, before I go on to explain what this code does, I want to just break this down a little bit. So the first thing is that this is a condition. So S equal to 0 is a condition. That's why I'm using this double equals, which is the condition. It's a conditional operator. It's a comparison operator. So the single equals does assignment. It gives S a value, but I'm not giving S a value here. I'm checking S's value against the value 0. So that's why I use this double equal. So that distinguishes comparison from assignment. Second of all, my condition is inside parentheses, and that's part of the syntax. So if S is equal to 0, and again, I'm going to tab here again because I want to make clear that the following line of code belongs to the previous if statement. Then I'm going to say Y equals, and remember, I don't use the assign statement to assign a value to a registered signal. Y is registered, so I'm just going to assign it a value directly. So Y is going to be equal to the 0th bit of X. That's how this works. Semicolon. So that when I have this condition, I don't put a semicolon after my condition. I put it after the statement Y is equal to X0. Now, I want to say there are 3 other possibilities. So I am going to write else if. So the way this works is it will check first, is S equal to 0? No? Okay, let's see what the next condition I need to check for is. So now I'm going to check for S equal to 1. So again, 2b1 is the same thing as saying 2b01. And then again, close parenthesis, I'm going to tab. I could put it on the same line also if I wanted. And it's equal to X1. Okay, a word about this. If I had more than one statement inside any of these, inside any of these else blocks, what happened here? So if I had more than 2 statements inside this else block, I would use this, I would use begin and end. Oops, I keep using Mac keys, but I'm in Windows. So I could do this. I could do begin and end. So if I had more than one statement here, I would be obliged to use begin and end to encase all those statements inside a begin and end block, just to indicate that all these statements belong to the else if above it. It's not necessary if I only have more than one statement, but I just wanted to bring that to your attention. So if I wanted 2 conditions to execute, if this condition evaluated to true, then I would have to encase them inside begin and end. So finally, I have another else if. So else if s is equal to 1, 0, then y is equal to x2. Finally, else if s is equal to 1, 1, which is 3, then y is going to be equal to x3, the third bit of x. Again, I'm using my vectorized notation to refer to individual bits in the vector signal x. So I'm going to have a catch-all just because, first of all, I want to show you how what the syntax is for this, and also you may be wondering, well, what are the other possible values for s? And it turns out actually they could be either z, which is high impedance, or they could be x, which is basically unknown. So I'm gonna, and they should not be either any of those things, but just in case, let's just have a catch-all, because also I want to show you how that works. So else is the condition that's going to evaluate to it, the statement that I specify inside the else block is going to be executed if none of these other conditions evaluate to true. So the way it works is it starts off with the first condition, checks the first condition. If the first condition is true, it's going to execute this statement, then it's going to exit, and we're done. If this condition evaluates to false, it's going to come down to the next condition. It will evaluate this. If this condition evaluates to true, it'll execute this statement, and then it will exit. But if it evaluates to false, it'll go down to the next condition, and so on. And if none of the conditions match, then it will do whatever I specify under else. So I'll just assign y the value 0. So y is 1 bit wide, which is why I have 1, and I'm specifying binary 0. And that's it. And this is my code. I will show you now what happens here. Notice that I'm no longer using my mux 2 to 1. In fact, it will not be implemented at all on my basis board when I generate the bit stream. In fact, because only the top module and all the modules that it instantiates, whether directly or indirectly, so all the modules in this hierarchy, those are the only ones that are actually going to be implemented on my basis board. So that's it. I've implemented my 4-to-1 mux. I am going to open my elaborated design. I want to look at my schematic, and I want to make sure that it should look pretty much the same with some changes. So let's see how it looks. So here I have my top module, which is just my mapping from my board pins to ports in Verilog. And let's take a look what happens here. So I've got a whole, but this looks slightly different than what I had before. So before, what I had were logic gates, and you can see now that actually I just have a whole series of muxes. So basically, depending on the value of s, it will select a different value for that mux. So, so this is what it looks like here. So in fact, I see that my 4-to-1 mux is composed of 4 individual muxes, which is interesting. So I'm going to show you an alternate way to do this, actually. So let's close this. And I'm going to show you an even better way to do this. So because this is combinational, so we haven't talked about any clocked or sequential designs yet, but because this is combinational, essentially anytime there's a change in the input, I want it to be reflected immediately in the output. And here I specified, like I said, a comma separated list of signals. But an easier way to do that would be to basically just use what's called the wildcard character, which is the star. And that tells Verilog basically any signals that are referenced here inside this block, if they change, then just trigger this code to run. So basically, it's exactly the same uh, effect as what I had before, as me specifying X and S. So because here I check S, the value of S, and I assign Y, the value of X, if any of these change, that will be captured here in this wildcard. So other than that, I'm going to remove this and I'm going to show you a different way. So because if you noticed in my if statement, I was always just checking the value of S. So another way to do that in Verilog is I will say I use this case keyword. So what that does is it's going to look, it tells Verilog, look at the value of what I'm passing you here. So I'm going to pass it the value of X, and then, oops, don't know how that happened, case S, and then it keeps doing that. And then it's going to terminate with an end case. And the way it works is this, and this is exactly identical to the if-else statement that I had earlier. So what it does is it kind of evaluates S, and what I do is I give it all possible values for S. So for example, 2B00, and I'm going to put a semicolon. I'm going to show you, I'm going to just put all my values for S, and then I'm going to show you this. I'm going to complete my code, but first I'm going to put all possible values. And then I'm going to put a default. So this is what happens if S is not any one of these values. So basically, this is equivalent to my last else clause in my previous implementation. And this is equivalent to saying if S equals 2B00. And then I follow it with a colon, and I can write all the statements that everything that I want to have happen here. And what do I want to have happen? I want Y to be equal to X0. And here, if S is equal to 2B01, I want Y equal to X1. Now I'm regretting having deleted it instead of just commenting it. And then, again, here, in this case, Y is going to be equal to X2. And here, Y will be equal to X3. And the default, we said, well, Y will just be equal to 0. So this is exactly the same as what I had before functionally. However, it's just somewhat more efficient. It's also clearer to read and clearer to look at. And I can do this because basically in each case here, so that's why it's called the case statement. So in each case here, I'm really just looking at the value of S, and I'm seeing what all the different possibilities are. And depending on what the value of S is, I will perform the specified statement here. So that's it. I'm going to save this, and I'm going to generate the RTL schematic also. Let's take a look at what that looks like. So let's expand this, zoom to fit. And here actually you can see that this looks slightly different. So now I really do have a 4-to-1 mux in my 4-to-1 mux, which actually makes sense. So it's really just implementing a 4-to-1 mux. You can see that actually even the schematic looks similar to, it looks actually more efficient to what I had before. So it looks slightly different. Functionally, it'll be identical, but actually at a glance now, I can see that my 4-to-1 mux is doing exactly what a 4-to-1 mux looks like. This is exactly the schematic of a 4-to-1 mux. So, so that's it. This is just another way of implementing my 4-to-1 mux using an always block. And stay tuned for next time when we will start implementing sequential designs.